In first video, we first discussed about why to make our own operating system. Then we added a user into it. We saw how user logs into a Linux system. We also discussed about how bash works. We also saw the importance of environment variables. Basically, we prepared our host operating system to make our own operating system. In next video, we talked about toolchain, how exactly toolchain works, how to make a toolchain, how to compile the packages with the help of configure, make and make install. We also talked about the difference between a package manager and a source package, the importance of API and the importance of glibc. In third video, we talked about a pass1 and pass2. In this video, we will be compiling the remaining packages and will be preparing virtual file system. Let's start. Welcome to part 4. So if you have observed in first 3 videos, we have installed only 10 packages, not more than that. And as we know that we need to install near about 84 packages. With this speed, it will take months to make our own operating system, that to a command-based operating system. What I used to do, I used to take one package, then I used to tell you the entire configure command, then I used to tell you make, then I used to tell you make install and all. I used to explain you each and everything. There was a reason behind it. And the reason was very clear that you should understand the structure. Once you understand the structure, it's very easy to install and compile the packages. There's nothing. Where is our host operating system? Where is our virtual machine and all? What are the contents of sources directory? What are the contents of the tools directory? What is the purpose of sources and tools directories and all? If you have understood it correctly, and I hope you have understood it correctly, then now on whichever package has to be installed, the structure remains the same. The configure, the prefix will be tools, then make and the make install. Some configuration files will be changing, some symlinks will be making, that will depend on the package to package, but the structure remains the same. So what I'll be doing, instead of taking one package and then installing it one by one, what I have done, I have written one script. So let me show you the script first. So this is the script. I made 4 scripts. So this is the first one. As you can see, a very easy script. There's nothing, a bash shell script. So what I'm doing here, I'm taking the package. First package is ncases, that's the next package which will be installing. Then you can find out I have copied the command which is a configure from the LFS 7.2 book. And after configure, as usual, make install. Then I will be deleting these packages. As you can see it here, I will be deleting these packages. And then I'll move to the next package. Then again same story, first untar it, next configure it, make install. Next bzip package, tar, make install. Move next, core utils, untar, configure, make install. This is what I will be doing. Before I start, you need to understand what I'm doing here. See, in this window here you will find I'll be running this command called as telf mnt-lfs-out. So here I will be running my script, which is a core0.sh. Remember, this is my custom script. Anyhow, I will not be providing this script. There's a reason behind it, and the reason is very clear. If you not install each and every package manually, you will not understand the importance of that package, what binaries that package provides and all. So I will highly recommend do it one by one manually. Okay. So this is how I will be running it. core0.sh I will be running, and then the core.sh output will be printed here. I'm redirecting the output to this atto.out file, and I'm just opening that file. Core.sh, whichever error message it will be throwing, those error messages will be going to the atto.err file, atto.error file, and the output, the normal output which we used to get on the normal screen, that output I redirected to this window. So this window will show you the actual output, and this window will show you the error message if you are getting any. And this will tell you what commands we are filing. That means configure, make and make install. My VM has a 2 CPUs and 2 GB around RAM. On this machine, this particular core0.sh script will be taking 15 minutes around. Okay, so let's start and hit the enter. Here you go. So as you can see, I'm installing ncases is the first package I'm installing, and then this is the configure. The first configure, let me run this. As you can see, the output you will receive at this end. That means the make is going on, and the make's output is here in this window. And if at all, if I'm getting any error message, that error will be captured here. Clear? That is how it is. So first package is ncurses. What ncurses does? Ncurses helps you building a command-based GUI, network manager, that to a CMD, a CLI network manager. That kind of windows you will be getting through the ncurs. Ncurs will help you on that. File a configure, you can see there is a prefix tools, and same story. We are installing the ncurses package into the prefix, into the tools. Going next, ncurses has been installed. We are going next with the next package, that is a bash. Obviously, then bash is, we all know that it's the shell. So this is the first time we are installing a shell of our operating system inside a tools directory. Next is we untar the bash source file. Then there is, we went inside the bash directory and we hit the configure. As you can see, we are installing at the tools. Then we hit the make install, we deleted that. We went for the next package, which is bzip2. We all know the bzip2, that is a zipping package. Then the next package which we are installing is the coreutils. That is one of the important package. Coreutils provides a lot of packages. Those are like, you know, cat, head, tel, split, WC, MD5 some sort, unique, ls, dr, cp, dd, mv, rm, ln, mkdr, rmdr, chown, change group, change mod, df, du, pwd, det, uname, uptime, chroot, nice, kill, sleeve. There are so many packages coreutils provide. Next one is the diffutils, which provides the diff binary. Next is the file, which provides the file binary. Next one is the find util, which provides the find, gawk, the beta version of awk, that. Next is get text. It will help you in native language support. Now the next package is grep. Grep, we all know that it provides the grep binary. We are installing as usual into the prefix tools. So far I believe we reached up to 22nd package. Grep is the 21st package, I believe. So from 10 we reached up to 21st. Next package is gzip. Again it's a zipping utility. Then after gzip, the one which we are installing is the M4, that is the macro processor. That is what we are installing. Then after M4, we are installing a make utility. So now concentrate. Make utility, the one which we used to use, because if you remember earlier while configuring our bin util, GCC and all, we used to use a make. That make binary we use of a host operating system. That is our CentOS operating systems make binary we use. Here we are installing our own make binary into the tools bin. Okay, clear. After make, we are installing, we installed a patch utility, that is for the patching purpose. Next is we are installing a Perl compiler or a language, the entire language suite we are installing, that is Perl. So first we enter the Perl directory, we went inside that and we hit the configure. So Perl is a big package, it will take some time. So now we hit the command make. So we are done with the make. Next package which we are installing is the set, that is the stream editor. We all know that. Installing inside the tools. We're done with the set. Now we are installing the tar package, which will be providing us a tar binary, obviously. Installing it inside a tools directory. Now we're done with the tar. Now we are installing text info package, that is for reading and writing the info pages. That's what we are installing. So as you can see, we are installing all the utilities which normal operating system provides. Now the next package is util-linux. As you can see, util-linux is a very important package. It provides all the system utilities which we use in our day-to-day life in Linux system as a system administrator. Commands like exec, blkid, dmessage, fdisk, then fsck, fstab, hexdump, ipcs, kill, last, mkfs, mkswap, mount, rename, su, swap off, swap on, umount, etc. So coreutils and the util-linux package, these two packages are very important. These are the two packages which provides you all the system related utilities or the binaries which you find inside Linux. These two packages provides you all this. Okay. So we are installing xz now, again the zipping utility as we know, and this is our last package which we install through our script. As you can see, the script makes your life very easy. So within this 15 minutes we have installed near about we reached up to 31st package. So we started from, I believe, 11 and we reached up to 31st, and we are done. So let me show you the tools directory. Inside tools we have the entire tree almost ready, which is bin, etc, include, lib, man, sbin, share, var, almost everything is ready. So if I go inside my tools bin, you will find all the binaries whichever we have installed so far. For example, cc is provided by the gcc, the next is cpp provided by gcc again, so all of that. For example, diff provided by the diff utils, expect provided by the expect package, then here is a find command provided by the find utils, file by file package. All of this packages we will find m4, make, all of this. Clear? I hope you understood this. So the next file which we need to understand is the virtual file system. So let's move to whiteboard. Virtual file system. So we need to understand first why we need a virtual file system. So the way we have ext4, the way we have xfs like file systems, the same way we have a virtual file system. That means the file system which will be present inside a RAM. XFS and ext4 will be present inside your disk. You'll be taking a disk, creating a partition on it, and that partition will be formatting with the ext4 or XFS. Whereas the virtual file system will be present inside a RAM. That means the moment you restart the system, this is gone. The virtual file system will be gone. Then the disk-backed file system has some advantages. The same way virtual file system has some advantages. Both of them has their own disadvantages as well, pros and cons. So the advantages of using a disk-based file system is that data is permanent. But the disadvantage is this is much slower, not much only, 1000 times slower than the RAM. Whereas in the RAM, the advantage is it's 1000 times faster than your hard disk, but the problem is it is not permanent, right? So you need to decide which data will go inside a disk and which data will go inside a RAM, inside your virtual file system. Now, the data which is not ever changing, or basically the data which is not necessary to access continuously, that data should go on your disk. For example, a user's data, for example, user some file, or if you're storing a movie, that should go on your disk. But at the same time, if a user is requesting to the kernel, show me the CPU usage or show me the memory usage, that time that data should not go on your disk, because this data, this particular CPU usage and memory usage data is ever changing. Every CPU cycle, after every CPU cycle, the data will change. I mean, in a second, kernel will check minimum 1000 times. I'm just giving an example. It will check 1000 times. It will go on the hardware. It will check the CPU usage, memory usage, and then it will bring that data back and it will give it to the user through virtual file system. So that time, kernel will not choose your disk-backed data. It will choose the one which is virtual, which is reside in your virtual file system. This is why we need a virtual file system. Where you need a highest throughput, there you use a virtual file system. Now we need to figure out what are those data and what are those virtual file systems. So in LFS, there are so many virtual file systems, but in LFS, majorly we're using 4 file systems, virtual file system. First one is the tmpfs. You might have heard about tmpfs. Next one is proc. You might have heard about the proc. Next one is sysfs. And the last one is the devpts. These 4 virtual file systems we'll be using. Okay. Now I will not go deep into these virtual file systems. For example, difference between tmpfs and devpts, tmpfs and some other ramfs like file system. I won't go deeper into it, but because that is not the part of this session, that is not the intention of our LFS. So if you're looking for virtual file systems information, then subscribe to the channel and I will make another video, separate video only targeting the virtual file system. There I will explain everything about virtual file system. Come again. Now, these are the 4 file systems which we'll be using inside the LFS. Now let's talk about the first file system, which is a proc. Okay, you might have heard about proc. You might have seen a directory inside a Linux operating system which will be present inside your root file system called as a proc. So that proc directory is actually your virtual file system. So you have a virtual file system called as a proc mounted on /proc. Clear? Now let's talk about how does it work. So you all must have seen this diagram. This is called as the operating system architecture. You have a hardware, on top of that you have a kernel, on top of that you have a shell, and then there is a user. User interacts with the shell, shell interacts with the kernel, and kernel actually controls the hardware. So kernel is equal to operating system is equal to kernel. Shell in the sense not only where you type a command, shell could be anything. Shell could be your VLC media player, shell could be your Google Doc, shell could be your web browser, it could be Firefox, it could be Chrome, whatever you see with your naked eyes, that's called as a shell. Whatever you don't see, that is actual operating system, which is a kernel. Now, user space applications, that means the one which we just talked about, the shell cannot directly talk to the hardware, or shell does not have any control on a hardware. Who has a control? It's the kernel who controls the hardware. That's the reason it's called as an operating system. Now, if shell wants some information, or shell wants to see some hardware information, for example, shell wants to see, or application wants to see a CPU usage, a live CPU usage. Okay, let's take an example. You are writing a top. Now top becomes a shell. It's a binary, it's an application. So application does not have access to the actual memory or actual CPU usage. You do not have access on that. It's only the kernel. Now what you will be doing, you will be calling some system calls. You're calling the kernel and you're asking the kernel, give me this and this information. Kernel will go to the hardware, it will check the hardware data, it will collect that hardware data, it will give it back to you. Okay. Now that data which kernel has calculated, kernel should not keep that data inside a disk backed up data, because the data which we are asking is ever changing data. Every CPU cycle, in every minute, in every second, in every microsecond, the CPU usage and memory usage will be changing. So kernel has to go back and forth continuously, check the hardware data, give it back to the user, check the hardware data, give it back to the user. That it has to do continuously. It's ever changing data, so you need a more throughput. So obviously kernel will put that data inside a virtual file system. In this case, it's the proc. Why the name proc has been given? Because all the process related data you will find it there. So for example, you are running a VLC media player and you want to check the memory usage of a VLC. You go inside your proc, you will find a PID of that VLC. Inside that PID, you will find a CPU and memory related information or the usage of the VLC media player. So we'll be mounting the proc file system with a proc file system itself. So proc/proc is your mount point, and we will be mounting it with the procfs. Next file system is sysfs. So what is sysfs? You might have heard about sysfs. You'll find a directory inside a root file system /sys. So what data you will find it there? Same story. The way we have a proc, the same way, for the same reason we have a sysfs. In proc you will find the process related data, but inside a sys you will find a drivers related data, or more precisely a device related data. For example, you're looking for a firmware version of your system. You have a laptop, you're looking for a firmware version of your laptop. That kind of information you'll find it there. You are looking for, you have graphics card connected to it, you are looking for graphics card related information, you will find it inside a sysfs. Clear? So kernel will check that all data, it will dump to your sysfs. So you'll be mounting a sysfs as well. Going next, we have a run, which is a tmpfs. So run is again a mount point /run. The way we have a /proc, the way we have /sys, the same way we have /run. Now this run is specific to system related systems mostly. Okay, since we are building our init based system, ideally we don't need a run. Nowadays, for two reasons, run mount point is getting used. One is for the systemd purpose. Another one is like Fedora and all, they mount the media. If you insert a DVD, if you insert a pen drive, if you use a USB, that will be automatically mounted inside /run media. So run will be mounting with the tmpfs. I hope this is clear. Now if this is clear, let's move next to the next file system, that is devices. Now you might have heard about one statement. That statement says for our operating system, hardware is a file. Come again. For our operating system, hardware is a file. Come again. The actual statement is for a Unix and Linux, hardware is a file. Now that's a true statement. That means what? The system which I use, that system has a 36 core. I bought that particular CPU around 1,35,000 rupees. That's hell lot of money. For me, for a user, it's a 1,36,000 rupees of a CPU, but for a Linux, just one file. And that file you will find inside devices /dev CPU file you will find. So I have a 36 core, so most probably I will find 36 files starting with CPU 0 to the CPU 35. 4K 34-inch monitor, a curved monitor and all, but for operating system it's just one file present inside /dev. There are three kinds of files you will find it there. A character spatial device file, you will find the block spatial device file, and you will find the pipe spatial device file. That means what? Character spatial device, you have a monitor, that is a character spatial device file. You have a hard disk, that's a block spatial device file. You open a file and you pipe it with the grep, that's pipe file. You will simply using a mount command to mount the proc, sys and run. But for the dev, we will not be able to do it. Why we will not be able to mount it? Because for that we need to understand how dev file system is getting populated. Whenever you boot your operating system, it's the kernel who detects your hardware. Whichever hardware you are connected to your system, whichever hardware is present on your system, kernel detects it and populates it through the udev inside your dev. Now what udev, I don't want to go deep into it. I will have another video for the udev. Stay tuned for that. For the sake of example, let me tell you very quickly what exactly happens. So kernel detects the hardware, then it tells the udev through the u event that this and this hardware has been I have found this hardware, and udev on behalf of kernel, udev will create a file, whether it's a character block or whatever the pipe file inside a /dev. Now the problem here is all will happen when kernel will detect the hardware. For that we have to boot our operating system. The kernel has to be present there. But the point here is we haven't installed or we haven't compiled our kernel yet. Then obviously we don't have our own kernel. Until and unless we have a kernel, you will not be able to populate the devices. What we can do here is we have a host file system which is CentOS. Inside CentOS, we are creating our own operating system, which is a LFS. So this CentOS, this hardware and the hardware which is inside your VM is same, right? When you booted this CentOS 6, this operating system's kernel must have detected the hardware and it should have populated, it should have populated the device files inside this host operating system /dev. Clear? So what we will be doing inside our LFS, we will be mounting the /dev which is already populated by this operating system, the /dev of host inside our operating system. So what we'll be doing for that, we'll be using mount with the option bind. So what this bind will be doing, this bind will be binding our /dev directory. Our directory will be what? /mnt/lfs dev. So what we will be doing, we will be mount the /dev of host operating systems /dev on mnt/lfs dev. All the files which are populated by this operating system's kernel will be automatically present will be available to our operating system. So what is devpts? Basically this devpts file system is a very special file system which will be present again inside a dev, right? So let me draw that diagram for you so that it will be easier for you to understand. So we have a /dev, and inside /dev there will be a directory that is pts, and this pts will be mounted by devpts file system. So this dev has tmpfs which we just talked about, whereas this pts, the directory which is present inside a dev, which will be having devpts file system into it. So what this file system does, devpts. So you have a shell, right? It's called as a pseudo terminal. Again, this PTS is called as pseudo terminal, not the shell exactly. For example, you have two terminals running on your system. Inside this terminal number one, you run a VLC. Through this terminal, the first terminal, you run a VLC. Through another terminal, you run a top command. So you have two binaries running. You have two applications running. One is VLC, another one is top. If I close this bash, if I close this terminal, what will happen? The associated binary or associated program to this terminal is VLC will automatically get closed, right? The same way for the terminal number 2 as well. So we have two terminals. So these two terminals are again considered as a separate hardware. Terminal number 1, terminal number 2. This is devpts1, this is devpts2. These two files will find inside devpts. 10 terminals you open, you will find 10 terminal files inside devpts. So now what we'll be doing, we will be mounting and populating these 4 virtual file systems. Let's do it.
First of all, we need to change the ownership of our tools directory, which is LFS tools, from a LFS user to the root user. So that's what we were doing first. Why we are doing it? It's very simple. Earlier, whatever commands we fired it under the credentials of a LFS user. But now on, all the commands which we will be firing, we will fire it under the root user. Now, root user of a host operating system. Okay, so there is a reason behind it that we will see it in next video when we will discuss about the chroot, which is changing root. Next, now we need to create the mount points for our virtual file system. That's what we are doing. That is dev, proc, sys and run. So we created 4 mount points. Going next, we need to create 2 files, 2 device files under LFS dev. That is dev console, and next one is the null. Those are character device files. These 5.1 and 1.3 are the major minor numbers. So mcnode is the command to create the device file. The way we create a text file through touch or through the cat command, the same way you create a device file through the mknode. Next, we need to bound host operating systems dev file system to our LFS dev. So as you can see, earlier LFS dev was empty. But now the moment we will bind it to the mount command, you will find the LFS dev has been populated, and you will find the same number of files which were there inside our host operating systems dev. The same number of files we will find inside LFS dev. Next one is, as you know, we need to create or mount the devpts file system inside devpts. GID is file, that is group ID, and the permissions which we are setting to the /devpts directory is 620. So to understand the devpts file system, let me open another terminal. So I just opened another terminal. Let me log in. Let me become a root user. Now I'm a root user of the host operating system. So this is you can see there are 2 terminals. And if I say hello to one of the terminal, which is terminal number 5, the moment I hit the enter, you will find the hello has been printed inside another terminal. You can see it at the background. Let me do it again. As you can see, the hello is getting printed at the another terminal. Now let me type there how are you. You will notice it's actually getting printed on another terminal. So devpts 5 is another terminal where you are seeing those hello, how are you like words. This is our devpts number 5, and where we were typing hello and all, that was our devpts 6. I hope now you will understand the importance of devpts file system. Now let me move next. Now we need to mount the proc file system on our LFS proc. Same way, let me mount the sysfs on our LFS sys. And this is our tmpfs we are mounting inside our LFS run. And lastly, if the /dev shm directory is not present inside our LFS, then we will be creating it. So this is it for this video. In next video, we will be discussing about chroot, and we will be installing the remaining packages. This is Yogesh Babar signing off.